my gosh, this baby is so not happening. Okay, that was Miss Yarbrough trying to sound like a crying baby. Did I sound like one? But anyway, what does this have to do with our upcoming chapter? Well, this is the thing. Every baby that's been born since 1952 deal with what's called an Apgar scale. Now, I've jumped to the bottom of page 1, and then I'm going to go back and give you the above notes. But it connects how what's called discrete random variables, which is what this chapter is about, what it has to do with everyone that has ever been born, definitely in the United States, how they were able to determine your health when you were born. They use what's called an Apgar scale. Now, I mentioned something that's kind of new. I said how discrete random variables, their association with this Apgar scale. So, what is a discrete random variable? What is a random variable? Well, let's go back. On this video, I am going to be talking about probabilities and discrete random variables. I'm going to also be talking about how to calculate and interpret the mean, which is also referred to as an expected value of a discrete random variable. But before I do, I need to talk about what a random variable is and then a discrete one. Well, a random variable, as you can see here, are values or numbers that describe an outcome. So with that last Apgar situation I gave, if you had a chance to read it, on the scale they scored anywhere 0, 1, and 2. And as they scored 0, 1, and 2, that was in 5 different categories. So once they added everything up, a baby can score anywhere up to 10. Now you also read that with that Apgar score, as I slide back down for a minute, that here the Apgar, are using whole numbers between 0 and 10. And we use this to evaluate the health of a newborn. So, these are just numbers. And now, since we're talking about statistics, these numbers have a specific name. They're random variables. But as we continue, random variables that are given on a probability distribution. So here, let's continue going about our notes. What is a probability distribution? Here, it states possible values of discrete random variables along with their probabilities. So in other words here, if I have a random variable that's x, I'm going to find out what's the probability of x occurring. That's what it means. Okay, so as I look down at my Apgar scale, I have a person or a baby that has an Apgar value of 0, then that occurred 0.001% of the time. And unfortunately, with that means that child perished. But let's not talk about that because that's really depressing. Let's continue with the statistics and we talked about what a random variable is. Let's talk about one that's a little bit more specific. A discrete random variable. It's a special type of random variable in which the probability right here goes with a random variable. Okay. Now, when it comes to this, they're usually whole numbers or integers that represent it. Another idea of a discrete random variable is your grades. Instead of saying A, B, C, D, don't we say 4, 3, 2, 1 to represent an A, a B, a C, and so on? Those are discrete random variables, and from there I can come up with probabilities. But before I do that particular idea, let's go back to now where we started, the idea of an Apgar scale. Please take a minute to read this. Okay, now that we're back, as I mentioned before, we are trying to test the health of the baby. The scale is 0, 1, and 2. They have 5 criteria, and the 5 criteria are skin, color, heart rate, muscle tone, breathing, and response to stimulus. What they do with the response for stimulus, if they have the little baby's foot right here, and they take a little object and they do this, and if their toe wiggles, this is the baby toe, then we know. Then they grade it according to how the baby reacted. So that's when they're referring to response to stimulus. The other ones are pretty obvious. But this is something that we use today to evaluate it. You can ask your parents. They did it for them. They did it to them if they were born after 1952. And they did it to your little brothers and sisters. Remember, I said they did it to you. So right here, I have a list of here are the scale values from 0 to 10 and the probability of probability of babies that scored this. Okay, so the research was done here for 2 million newborns in a single year. Now, before I continue, I took this straight out of the 5th edition textbook. For those of you who have it, this is from page 349. And normally I don't take problems straight out of the book. I mean examples that are done. But I'll be honest, even though I'm a statistics teacher and I've obviously given birth, I've had 2 kids, I never really thought of an Apgar scale as a discrete random variable. So I'm like, this is perfect because this is applicable to everyone. Okay, so you have your chart written down. Please recognize that this is a probability distribution. So here is the probability distribution. So like I said, it stated all possible values, discrete values, and the probabilities associated with it. Now, just like in the past chapter, we had to see if it was a true probability distribution. So to see if it's a true probability distribution, okay guys, I had to pause and I really don't remember where I was or what I was saying. But this is the bottom line here. Just like what we did in the prior chapter, in order to determine if something, see you later, in order to determine if something was a probability distribution, all the probabilities had to add up to be 1. Okay, had to stop that. So here, the probability distributions add up to be 1. So here, you look at all of these that are listed here, and you are just going to do the mundane task of just plugging them in and see if it equals 1. So here, you've got your 0.01, your 0.001, your 0.006. You're going to write down the rest of them, and I'm just going to put ... Then the 0.053. And when you add them up together, they do equal 1. So that's a check. So therefore, it is a probability distribution. So the next thing I have to do, okay guys, I'm sorry I was interrupted again and I don't remember what I was saying. But I wanted to say, okay, we've done the checking. The next thing we're doing is making a histogram. So as I make a histogram for this, remember a histogram is a bar graph in which the sides are touching. So right here, my discrete random variables go here. So this is 0, 1, 2, 3, and so on and so forth. Okay, my probabilities go up here, the probability of the discrete random variables. So here I'm going to make that a 10, 20, and I'm going to move up all the way to 50. Okay, of course I ran out of room. And then I look at my table. Well, my table says that the probability of, where'd it go? The probability of getting a 0 is less than 1%. You know, thank God for that, right? So that's going to be about here somewhere, meaning it's a blip. The probability of 0.006, another child, unfortunately, that's going to probably perish. Okay, just slightly higher, just slightly higher. And you're doing the same thing. I'm just going to go ... I'm going to show you a complete graph in a minute. Okay, but what about once I get to that 10, or I should say that 9.437? Okay, so now here is your final product. As you can see, here are the discrete random variable, which are the Abgar scores. I don't know if you can see that right there. There's the probability. And for that one that I was saying, the Abgar score that got a 9, which most babies are, here is your 0.43 and whatever the rest is. So take a moment and draw that histogram and then continue the tape. Okay, so this next question is, they say here that an Abgar score of 7 or higher indicates a healthy baby. So we want to find the probability of the occurrence of getting 7 or higher. So let's now look back at our chart. And the probability of 7 or higher are going to be these values right here. Your 0.099, your 0.319, your 0.437, and your 0.053. So as you can see here, the probability of 7, the probability of 8, the probability of 9, plus the probability of 10, which is going to equal 0.908. And that's it. That's all we have to do. Okay. Now remember here they said x is, the discrete random variable is greater than or equal to. So we do have to include this value right here, the probability of when it was 7. Now, next, what is the mean of a discrete random variable? First of all, we know the mean is nothing but the same as an average. But now they've thrown some new symbols at us. So here, you've got the average, which is saying the mean sub x. And we're going to talk about how this is done in a minute, but what it's saying is that we take each discrete random variable and multiply it by its probability. So, in other words, as I look at your problem down here at the bottom, they're saying I'm going to take 0 times that, plus 1 times that, plus 2 times that probability, 3 times that probability, 4 times that probability, and you're going to do this all the way out, and then you're going to get the expected value or the mean of these discrete random variables. And I use the term, the upcoming term, the expected value. So first of all, whenever you see that e of x, that is your expected value, and the formula is exactly the same. The summation of, once you multiply the discrete random variables times the probabilities. So the formulas are the same. Okay, now, I want to do 2 of these. So the first one, I'm going to call this one 2A right here. I want to let y equal the spots on the side showing. And I want to make a probability distribution. Okay, so here we know my dice has 6 sides. We know that the probability of the 6 sides are equal. And this is, what we've done now is I have found a probability distribution. Now this is not the same as the directions. That's why I'm calling this 2A, and in a minute I'll call that 2B. They want us to make a histogram, but we're not going to make a histogram of this. I just wanted to show you this. You know what? I just changed my mind. Let's do the histogram. So here is your 1, 2, 3, 4. And we see that the probability is going to be the same You have to excuse my drunk looking. Oh my gosh. They should be the same going across. This is 1/6. Okay, so here's your histogram. And this is also referred to right here as a uniform distribution. And that's because here, all of our probabilities are going to be the same. Now that's 2A, one I just made up. But now let's talk about 2B. 2B is saying that we want to find the probability, we want to find the probability distribution of T, but T is the sum of the spots that show up. So let's make a chart. So my chart is talking about 2 dice. So here are the values of the first die. Here's the value of the second die. And then we're just going to take the sum of them. So all that I'm doing here, as I wrap this one up, 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3 is 4. That's where these values came from. So as I wrap this up, 6 and 4 gives me a 10. 6 and 5 an 11. And 6 and 6 are 12. Okay, so now here is my complete distribution. Now why did I do this way? Just because I wanted to? No other reason. Because it's going to be easier for me to come up with the different sums. Now let's look at all the values that I've got going here as I try to figure out what my discrete random variables are. Well, I've got a 2, then I've got 3, then I've got 4, then I've got 5, and I have 6, and I've got 7, and I've got 8, I've got 9, I've got 10, and I've got 12. Now the only reason I color coded like that was simply so you could see it. So here are my discrete random variables. Notice they're all, this is a 6 by 6, so that means it's going to be out of 36. So my denominator in all cases is 36. Then let's see, how many are 2s? There's 1 of them. How many are 3s? There's 2 of them. How many are 4s? There's 4 of them. And I know I can reduce this stuff, but I'm not going to, because if we got to find the sum of these discrete random variables and add together 1 plus 36 plus 2 plus 36 plus ... plus the last one, which is 1 over 36, and to confirm that it equals 1, why would I sit there and change my fraction to reduce it to have to change it back to get a common denominator? Think smarter, not harder, people. Okay, so here's my probability distribution table completed. And once I check it, yes, it does equal to 1. So it is a true probability distribution. And now I'm going to do my histogram. I'm using some graph paper so that my histogram comes out neat, because I don't have a pretty book copy like I did. Okay, so here I have this. And here's for 2 out of 36. There's another one that's 1 out of 36. Here's 2 out of 36, and then I'm just going to complete my table, complete my graph. Okay, so this is what I have so far. Oh, I had to change that up there. I made it a 4, so change it to a 3, please. And then let's wrap this up. And here is my histogram of my probability distribution. 4-part. Here, make the histogram of the probability distribution. And what we noticed on here was that this particular one for part 2B, it really looked like a bell curve. So it looks like bell curve. Next, when I want to find the probability of it be of the t, which is the total number sum that's as face up, that's greater than 5, and I want to interpret. So as I look at the probability that's going to be 5 or greater, I'm looking at all of these here. Then all I've got to do is add them up together. So my interpretation right here is that 81% of the time, or approximately 81% of the time, I'm going to get a value that's going to be greater than or equal to 5. Okay, now go ahead and read question number 6. Pause. Okay, so now that you're back, the sum of these do add up to be a 1, so therefore it is a legitimate probability distribution. I will be getting rid of that not equal to thing in a minute. Next, making a distribution. I'm going to start you and then I'll show you the better picture. So this is a 1. Your probability is here 2, 3. Remember your discrete random variables are here 0, 1, 2, 3. Okay, the probability of 0 is 68%, so that's going to be up high somewhere. Here is your 68%, which is about there. Bring it down about there. Your 1 is 0.5%. And then you just do it for the rest. Now here's what your graph looks like. And to answer the question, what does it look like? It looks strongly right skewed to me. It has a huge peak at 0 right there. Okay, so now as we look at part C, describe the event y is less than in words. So what we're saying here, this is the probability of them not working out at all during the course of 7 days. Unfortunately, that would be me. Got to work on that. Next, let's look at D. And let's describe, oh, and sorry, I forgot to mention, I've got the probability there, adding them up together. So asking the exact probability. So that's saying 98% of the people pretty much did not work out at all during the course of the 7 days. Yeah, welcome to my world. Okay, now, so let's look at part D. Okay, so now part D is saying express the event. We want the probability of it being greater than or equal to 1. Well, if we look up at our chart right there, we can see here are all the values that I have right here in pink that are greater than or equal to 1. So with the idea of, remember, thinking smarter, not harder, well, probability of it not being 1, so that's the same thing. So I'm just going to go 1 minus the 0.68. Okay, so I'm going to go ahead and do number 10, and we can talk about it if you want on the weekend. Now let's look at what I've done for this problem and why, the fire insurance. Okay, so here you spend $300, so that's why this is a positive amount. And the policy will pay out $200,000. So the company will earn $300. If it pays out the $200,000, that means they have a loss of $300 minus that $200,000. Now let's look at my probabilities associated with it. But before I do that, I want to try to say that one more time. Here, this is from a fire insurance's perspective. They get $300 from you. But if, heaven forbid, you need to use the policy, they're going to give you $200,000. So they lose $199,700 because remember, you gave them 300 of that. So there's the math on that. Now the next thing they said, from the previous data, the probability that a home area is destroyed by fire. Well, if it's destroyed by fire, that's how much the insurance company loses. And if that's how much they lose, the probability of them losing it, that means when I subtract 1 from this, this is the probability of gaining. That's where the 0.992 comes from. Now, as I look at my expected value, the formula that I gave before, let's use it. So here, the expected value of y is going to equal 300 times the probability of you getting the 300 plus a negative $1,999 and $199,000. I'll say this right sooner or later. $199,700 times the 0.0002. And once you do the math, you are going to get $260. Remember, we got this from our formula from the prior page. The expected value of x is going to equal your discrete random variable times the probability of its, well, times its associated probability. Okie dokie, guys. Have a great weekend. Long video. Sorry. It's been a good day, though. Talk to you guys later. Bye-bye.